Am I audible? Can you listen to me? So, about rotation with respect to some arbitrary axis or arbitrary line. As some of you have another session from 11 o'clock, so without any further delay, let's start. Let's start with 3D sharing. If you can recall sharing in two dimensions, it looked something like this. This was your two-dimensional space. Then you had a 2D object onto which you can apply shearing transformation either in the x direction or along the y direction. If you have applied shearing force along the x direction, you can recall that changes take place. One was x-axis shearing and another was y-axis shearing. In three-dimensional space, the concept is much similar, as there are three primary axes, viz. X, Y, and Z. You have to decompose your shearing task into three parts, namely shearing along x-axis, shearing along y-axis, and shearing along z-axis. Now let me dive deeper into the mathematical equations. If you apply shearing along x-axis, then x coordinate values actually don't change. Only change occurs in the y and z coordinates, and mathematically it will look like this. So assumption is that before you apply shearing transformation, your original coordinate values are x0, y0, and z0, and shy and shz are the shearing transformation factors for y and z coordinates. So as we have looked that once you apply shearing along x-axis, only the y and z coordinate values will be changed by their corresponding shearing factors. The equations will be like this. There will be no change in x coordinate value, hence x1 equals to x0. There will be change in y coordinate value like this. y1 equals to y0 plus shy multiplied with x0 and z1. That means z coordinate value after shearing transformation along x-axis equals to z0 plus shz multiplied with x0. Now if you want to convert this into a single equation involving homogeneous coordinate, you have to append homogeneous 1 equals to 1, and your entire set of equation will be like this once you convert this into matrix form. So This is your shearing matrix along x-axis. Shearing matrix along x-axis in 3D. Just take a note of this. Now let me look into shearing along y-axis. In this case, what will happen is there will be no change in y-axis or y-coordinate value. Changes will take place only in x and z coordinates. So once you apply shearing transformation along x-axis, your equations become something like this: x1 equals to x0 plus shx multiplied with y0. y1 equals to y0, no change in y coordinate value. z1 equals to z0 plus shz multiplied with y0. So just observe this set of equations, how the changes are taking place, and if you convert this to homogeneous matrix equation by appending 1 equals to 1, then you get something like this: vector x1 y1 z1 1 equals to, this is your shearing matrix along y-axis. Shearing matrix along y-axis. Here we go. Now the third portion is shearing along with z-axis. Now when you apply shearing transformation along z-axis, what happens? Like the previous two instances, there will be no change in z coordinate value. Changes will take place along x and y axis by a factor of original z coordinate value. Have a deeper look into the equation set. x1 equals to x0 plus, and this is the portion of the change which will take place into the x coordinate value by a factor of z coordinate value, shx multiplied with z0. Similarly, y1 equals to y0 plus shy multiplied with z0, and there will be no change in z coordinate value. Now if you want to convert the set of equations into homogeneous system, you have to append the homogeneous 1 equals to 1, and this is going to be your equation in matrix format. So this is your shearing transformation matrix along z-axis. So in 3D you can represent shearing transformation using these three matrices. Shearing, it is on. Something is wrong here. Just wait a second. Yes, it's here. You can represent shearing in 3D by using three matrices. Shearing matrix along x-axis, where it is. Then using shearing matrix along y-axis, here it is. And lastly, shearing matrix along z-axis, here it is. Now, this was shearing. Let's look at now rotation about an arbitrary axis in 3D. So in 2D, if you can recall, rotation used to take place with respect to the origin or by some arbitrary point. So if you had to rotate something with respect to this arbitrary point P, what you had to do? First you had to translate this point P to the origin, then you had to apply rotation with respect to the origin, then again you had to translate everything back at their original location by applying a reverse translation of the first one. Now in 3 dimensions, what happens? You know from our study of rotation in 3D that rotation can take place with respect to primary axis, which are essentially lines. So in 3D, rotation can take place with respect to some arbitrary line. So just imagine of this vehicle, it should be horizontal to the ground, or it should be grounded properly. Now look, which I have drawn right now. So once you turn this as a screw, your vehicle will be, this is your green line, is your y-axis. This red line, you can see it here, is your x-axis, and your, where is my pencil? Yes. Z-axis should be something like this. So this is your z-axis. You can see the z-axis is the vertical one. Your z-axis should look like something like this. So what is an arbitrary line? So now, before, what we used to do is, you used to do the rotation by this arbitrary, not arbitrary, sorry, some point which is located in your three-dimensional space. So our rotation matrices are established with respect to the primary axis, as well as the assumption is that rotation is done with respect to the origin. So first thing what you have to do is you have to shift this arbitrary line, which for the time being is not passing through the origin, to the origin. That means you have to shift this line somehow so that it passes through the origin. That means the transformation you need to apply onto this line is translation, so that this passes through the origin. For the sake of simplicity, let me move this object. Not able to move it. Leave it. Achha. So if you apply a translation such that this line passes through the origin. Now your line will be like this. Say it is L dash. So first step you have applied is translation. Then next step is to align this line with some of the or any of the primary axis. To do this, first what you have to do, you have to push this line onto some primary plane. You have three primary planes: xy plane, yz plane, or xz plane. You have to push this line so that it will lie on some primary plane. Now you can see that at this position it is not lying on any of the primary planes, any of the three primary planes. So if you push it like this, your line will be passing through the origin and will lie onto some primary plane, say onto the yes, like this. Now you can see that this line is lying onto the primary plane xy. Next step will be, so you can achieve this lying onto the primary plane by rotating this line L by an angle the line is making with this primary plane. You can see that this line L dash is making some angle with the primary plane xy. If you rotate this line L dash by an angle or by that angle, it will be onto the primary plane xy. Now your next task will be to align this line L double dash with your primary axis, say x-axis. For that you have to find the angle of the line L double dash with the primary axis x-axis. And if you rotate this line L double dash by that angle, now your line will be aligned with the x-axis. Now what you have to do? You have to do the actual task of rotation with respect to x-axis. Now you have the rotated point, but it is not at the place where it should be. So what you should do? You should again do a rotation so that line triple dash or entire system is transformed to with respect to L double dash. That means a reverse rotation. Then again you need to rotate your entire system by this angle, but this time in the reverse direction, so that entire system is transformed to the system which is defined by this L dash. Now lastly you have to do the reverse translation to put everything back with respect to L. So now I believe that you know the sequence of the operations. Let we look at the mathematical things briefly. First, you can define the line L by a vector xyz. So this is basically nothing but vectorization of a point on the line. So how it goes like x equals to au plus x0. X0 is the x coordinate of this starting point p0, y equals to bu plus y0, z equals to cu plus z0. And what is u? U is your directional coefficient, and if you represent a line in vector form, it looks like something like this. And a, b, c is basically the x distance, y distance, and z distance of a point from the origin. So your line L can be represented something like this. Root under s square plus b square plus c square u. So in another words, you can say that this length from P0 to P1 is defined by this value. This is simple geometric phenomena. If you give it some thought, you can understand it. So this distance is basically a square plus c square root over. Next, as we have discussed before some time, first you have to translate everything so that your arbitrary axis, that means in this case the line L, passes through the origin, and it can be achieved by this translation matrix. So the distance from origin O to P0, or in simple terms, the coordinate for point P0 is x0, y0 and z0. So if you translate this line by this minus x0, minus y0 and minus z0, then your line is going to be passed through the origin. Next, as we have discussed, you have to push this line or translated line so that it lies on the xy plane. You can figure out the xy plane here. So for that, what you have to do, you have to find the angle this line L is making with the xy plane. So from observation you can find it out. How? This distance is L, right? And so can you figure out this vertical distance? Yes, this is C. Sorry. Right? So from this simple thing, you can find this angle. How? So if you think of this as a triangle, let me draw the triangle in 3D space. So this distance is going to be root under b square plus c square. So in simple terms, if you try to find the sine theta and cos theta, say this angle, say this angle is theta. After pushing this line should be somewhere here. Your sine theta will be b over v, and cos theta 1 will be c over v. So if you rotate everything by this rotation angle, you will get your line onto this xy plane. Next, the diagram is not clear here. You have to rotate this line, which is now on your xy plane, say by an angle phi, so that it gets aligned with the x-axis. So for that, say this angle as per the definition is not phi, it is theta 2. So if you observe a little bit, theta 2 is going to be sine theta 2 is going to be minus a over L. L is the length of the line, and cos theta 2 is going to be v over L. V, this is v. So this is the second rotation which you need to apply onto your system or in your mathematical sequence, so that your arbitrary axis get aligned with the primary x-axis. Then simple rotation with respect to x-axis. Now the main rotation task is complete at the step 4. Now next task will be to reverse this rotation, in which we have aligned our arbitrary axis along with the x-axis. So for this, you need to rotate everything by an angle of minus theta 2. So this is going to be your rotation matrix. Then you need to rotate everything so that you get to this position, the position at which you have arrived after translation, so that your arbitrary axis passes through the origin. So in this case, your angle of rotation should be minus theta 1. This is going to be your rotation matrix. Lastly, you need to translate everything back so that you get your arbitrary axis back where it actually used to be. That means here. That means you need to apply a rotation by x0, y0 and z0. So this was the sequence of operations you need to apply if you want to rotate anything with respect to some arbitrary line. Just try to remember the steps, and this mathematical operations are a bit complicated, so give them your thought if you are interested. That was rotation about arbitrary axis, and here is your complete sequence of operations. Here you have an example onto which you can apply the mathematical formulas. And lastly, a disclaimer: this slide is not made by me, it has been copied from the internet. So That's the end of the tutorial portion. It's time for the quiz. So the quiz is rather simple. You should try to do it fast. Where is it? It is not yet public. I'm making it public. You can access it from Google Classroom. And also, I'm going to share the link in the chat box so that you can get it directly from here. Here is the Google Classroom link. Here is the direct link. It is 10:35, so I believe that 10 minutes will be enough for the quiz. So quiz will end at 10:45. Quiz ends at 10:45. So the quiz time is over. Um, I'm going to switch off the accepting responses button for now. Later on, you can attempt the quiz once again if you want. Uh, so the quiz time is over. Let's have a look at the answers. In shearing along x-axis, only y and z coordinates are changed. Uh, changed. The answer is going to be true here if you can recall the discussion in this portion. You can find that in shearing along x-axis, only x coordinate value doesn't change, only change happens in y and z coordinate values. Similarly, in shearing along y-axis, y coordinate value doesn't change, and change happens in x and z coordinates. And for shearing along z-axis, the z coordinate value remains same and x and y coordinates are changed. So the answer is true. And for the next two questions, in shearing along y-axis, only x and z coordinates are changed. This is again true. Correct it. And in shearing along z-axis, only x and y coordinates are changed. This is also true. Find the odd one out among rotation in 3D, translation in 3D, and shearing in 3D. Now, if you look into different transformations in 3 dimensions, you can find that for rotation and shearing, you actually need 3 matrices. For rotation, rotation with respect to x-axis, rotation with respect to y-axis, and rotation matrix with respect to z-axis. Similarly, for shearing, as we have done today, you have noticed that you need 3 matrices, but for translation in 3 dimensions, you need only 1 matrix. So the odd one is the second option, that is translation in 3D in that sense. Like 2D, rotation about an arbitrary point is possible in 3D. The answer is going to be false, because in 2 dimensions, rotation takes place with respect to some point, but in 3-dimensional space, rotation happens with respect to some lines. Rotation matrices are generalized in terms of the primary axis, x-axis, y-axis, and z-axis. And as you have noticed in today's discussion, rotation in 3D is possible with respect to some arbitrary line also. So the answer is going to be false. Rotation cannot be performed with respect to some point in 3 dimensions. You need some line. Yes, don't forget to write down your university roll numbers into the chat box for our attendance record, as we are near to end of the session for today. In x-axis shearing matrix, the item at location 0, 0 is. So for that you have to recall the x-axis shearing matrix, and the locations goes like this. Is your first column with index 0, second column, third column, and fourth column. First row, second row, third row, and fourth row. So the item at location 0, 0 is 1. You can see here. So the option is this one, second option. In y-axis shearing matrix, the item at location 0, 1 is, so let me revisit the y-axis shearing matrix once again. Drag it a little up. So the location at item at location 0, 1 is, you can see, SHX. So the correct option is the third option, SHX. I can see that into the chat box, Onavi, you have written your name only. Type down your university roll number. Last three questions. In x-axis shearing, the y-coordinate value is changed by some portion of x, y, or z. So for this, let me revisit the equations for shearing along x-axis. Here you can see that y and z coordinates are changed by some scaled value of x. Along y-axis you have added y0 to the scaled value of x0 multiplied with shy, and for z coordinate x0 has been multiplied with shz. So the correct option is the first option, that is x. শারবানি, আমি গুগল ক্লাসরুমে রেসপন্স করছি বাট তাও সাবমিট হচ্ছে না। Okay, you can do it later on. I have stopped accepting responses. I'm toggling it on, and you can try the quiz as many times you like. But only one thing you have to follow is you have to be honest. Just read the study material, go through the tutorial, then try to figure out the answers yourself. In rotation about some arbitrary line in 3D, the first step is translation, rotation, and scaling. Now, if you can recall the discussion here, you can find that for rotation about an arbitrary axis, the first step which has been followed was to translate the arbitrary line in such a way so that it passes through the origin. Hence, the first step is actually translation. Translate point P0 to origin O. And the last question, in rotation about some arbitrary line, the line should be aligned with any of primary planes, true or false. So again, if you follow the second step, of the algorithm, then you can find that after translation, once the line passes through the origin, then you have to rotate the arbitrary axis in such a way so that you get the line onto some primary plane. So in this example it was xz plane. So yes, the answer is true. In rotation about some arbitrary line, the line should be aligned with any of the primary planes. So that was all for today. I'm going to upload the study material as well as the tutorial video after some time into the Google Classroom. Later on, you can access the material. If you have some confusions, then read the study material, take notes, watch the tutorial, then attempt the quiz until you get 20 out of 20. All the answers are from the tutorial itself. So if you study carefully, you will be able to figure out the correct answers. And one thing, you must not copy the answers from the discussion itself. You should try to figure out the answers so that you get a sound understanding of the concepts. So that was all for today. Have a good day ahead. I'm going to disconnect myself now. Bye.